Hello, welcome to the video. In this lesson, we're looking at section 3.2, where we're going to learn about linear functions. So essentially today we are going to determine whether a particular function is going to be linear or if it's going to be not linear. If you look in the word linear, you see the word line. So essentially, anytime we are dealing with a linear function, when we illustrate that in a graph or on a coordinate plane, a linear function will represent itself as a line. So in this example here, we have two different graphs, all right, graph A and graph B. They're asking of us, does the graph represent a linear or nonlinear function? And they're wanting us to explain. So essentially, all you have to do is look at the graph and say, does the graph make a line? If you can say yes, then it is linear. If you say no, then it is not linear. So looking at example A, our graph is not a line. It kind of goes down here and it curves back upwards this way. It is not a line, which means that it is non-linear. Looking at example B, we do have a line on our graph, and since we have a line, we can say that for graph B, it is in fact linear. Here, they're asking us to represent a table, and they want you to know from these sets of ordered pairs, is our function going to be linear or non-linear? Okay, so when we look at a table, it is a little bit more not as straightforward than it would be by looking at it on a graph. So anytime you have a set of values for a particular function, it has to be consistent with essentially like a common difference. So here's what I mean by that, by having a common difference. So in this particular example, for example A, there is a certain pattern that goes with the x coordinates. So 3, 6, 9, 12. So everything on the table here is added by 3. So I added 3 here, I added 3 here, I added 3 here, and you would probably add 3 to the next set of ordered pairs in order for you to solve this problem. That's good. We have consistency there. We also, since there's consistency in the x coordinate, there has to be a certain level of consistency in the y coordinates as well for it to become linear. So if I look from first number of y, which is 36, to the second number of y, which is 30, it was subtracted by 6. So now the next sequence of events must also be subtracted by 6. 30 minus 6, does that give me 24? The answer is yes. 24 minus 6, does that give me 18? The answer is yes. So everything in the y part of the table gets subtracted by 6. So since I have a constant common difference with 3 and a constant common difference here with the negative 6 in both the x and the y, I can say that example A, yes, is in fact linear. Okay, it has to work in both the x and the y coordinates. So looking in example B, I do find that there is consistency in the x. If I add 2, I add 2, I add 2, there's consistency there with the x coordinates. Now, if I look at the y coordinates, between 2, I would have to add 7 to get to 9. Here, I'd have to add 9, or no, more than that, I'd have to add, looks like 11. And then looks like I'd have to add 15. See, there's no consistency here with the y coordinate, and since there's no consistency, it's not considered a constant. So since there's no constant value, it is considered to be non-linear. Okay. Here, this is a couple of examples to determine if a function is linear or not. One gives me a line, it's linear. Number two, it gives me a line, but there's like my line gets kind of cut off right here. So it's kind of a broken line, but it's not linear. It has to be one continuous line. All right, and here it says, which of the following equations represents a linear function? And they want us to explain. All right, so for the most part, anytime we are looking at a linear function or equation, it is going to be represented in what is most commonly known as slope-intercept form. So here it's going to be y is going to be equal to mx plus b, okay? Y is equal to mx plus b. A couple things that we have to take into account when we see a particular equation that could potentially look like a linear function or linear equation. For one, y, y is by itself, x is in the numerator, x is raised to the first power, and you have a constant value b, which in this case would be like the y-intercept. And we'll kind of get into uh, that a little bit as we move forward. So we have a series of different examples here. So I got y is equal to 3.8, okay? So for one, y is by itself, good, and then it's going to be equal to, and there is no value of x. So since there is no value of x, that's okay. It just means that it's represented as a horizontal line. So the answer is yes, this would be linear, okay? So I'll X that one out. That one is linear. I'm just Xing out that I worked out that particular equation. Y is equal to the square root of x, all right? Because x is not raised to the first power, it's got a square root to it. That means that it's not going to be linear. So this is an example of non-linear. It won't be represented as a line. Next, I got y is equal to 3 and it's raised to the x power. The variable x is an exponent. So because that is an exponent, this is an example of an equation that is non-linear. The next one is y is equal to 2 over x. X in this particular instance is in the denominator. Because it's in the denominator, that is an example of something that would not make a line, and that is non-linear. Here I got y is equal to 6 times by the quantity of x minus 1. If I were to distribute this, I would get y is equal to 6x minus 6, which basically looks like our general formula for a linear function. M is 6, B is negative 6, and looking at that, that would be classified as all of the characteristics that would be a linear function. And then finally, the last one is x squared minus y is equal to 0, okay? Now, y is not by itself, so what you would have to do is subtract x squared to both sides. So now I got negative y is equal to negative x squared, and then multiply or divide everything by negative 1. So it's essentially is y is equal to x squared. X in this case is not raised to the first power like it is over here because it's squared. This is an example of something that is non-linear. All right. This is one of the ways that you might be asked in order to graph a function, graph a linear function. So what they've done here is they give you the equation, and this equation is y is equal to x plus 3. What they would ask of you is they would ask you to plot certain points on the coordinate plane to first off determine if it is in fact linear. Okay, you know, we just looked on the previous slide. This was the general equation for a linear function with respect to slope intercept. Because it kind of looks like this, we can make the conclusion that it is linear. But this is how we show that it is linear and exactly the equation that we're looking for in a coordinate plane. So what we're going to do is we are going to choose certain values for x, okay? So what they did was is they picked some negative, some positive, and they also chose 0. And then what you're going to do is all of these numbers here get substituted in for x, and then you solve it to a result of y. So for like the first one, it's negative 1, which is x, is what they did here, plus 3. Negative 1 plus 3 is equal to positive 2. 0 plus 3 is equal to 3. 1 plus 3 is equal to 4. 2 plus 3 is equal to 5. So what we have here is a series of ordered pairs. Negative 1, 2. We have 0, 3. We have 1, 4. And we have 2, 5. And the points that we plot, or the points that we created, should form a line, and you can take a straight edge and make your markings from there. So that is how we can represent a linear function. Also in this section, we're going to talk about what are called discrete and continuous domains. So if you recall, domain is the set of x values in a problem. And anytime they're asking for a discrete domain, they are looking, it says, a set of endpoints, which means it's a set of x values that consist of only certain numbers in an interval. So like in this particular example, they're only looking at the integers. So the nice clean values, like counting numbers, both positive and negative. The next is talking about a continuous domain. Continuous domain is a set of endpoints, and again, set of x values, and which consists of all the numbers in an interval. So here they're saying all the numbers between 1 and 5, so that includes the decimal values, fractions, all the stuff that's inside there as well. And if you notice, with the discrete, they use points. With the continuous, they made a line in between them. So that's kind of where we can think like, all right, discrete domains are going to be looking at as points more than likely, and continuous domains is going to be shown up as like a line segment. So here it says we have a linear function y is equal to 15.95x represents the cost y in dollars and x in tickets to the museum. It says each customer can buy a maximum of 4 tickets. It wants you to find the domain of the function and is the domain discrete or continuous, and they want you to explain. Well, so X is supposed to represent tickets for a museum. Now, since since you can't have a fraction of a ticket, I would say that this particular one is a discrete domain, and the values are going to be integers. So it'd be like 0, 1, 2, 3, and 4. So they're all going to be essentially positive integers. And then it's asking you to graph the function of its domain. So what you could say, let's see if we get a graph here. So for instance, let's just say that these are in intervals, the y coordinates are in intervals of, let's say, we'll go 5 for the most part. So if I got 0 tickets, I got $0, you know, so 0 comma 0 in this particular instance. If I bought 1 ticket, well, you take 1 and times it by the 15.95, so that's where 15.95 comes in. So 1, and then so it's 5, 10, 15, so I'll just say it's right about there. Got 2, so if I bought 2 tickets, 15.95 times 2 is 31.9, so 5, 10, 15, 20, 25, 30, so it looks like it's right about there. And I'll do one more, 3, 15.95. So it's what, 47.95. So I got 3, so it's 5, 10, 15, 20, 25, 30, 35, 40, 45. So I'll say it's right about there. And you can kind of tell it looks like if I were to take a straight edge and all of those lines would connect. So it shows that it's linear, but because I stated that it was discrete, I'm just going to leave it as the points. Because again, you can't buy a fraction of a ticket. All right, so again, here this one says the linear function m is equal to 50 minus 9d, which represents the amount of money in dollars. And you have after buying D DVDs. So here it says find the domain of the function. It says is the domain discrete or continuous? It's asking you to graph this function. So here it says it represents the amount of money you have after buying DVDs. So looks like guessing each DVD is what, $9 or something. So or whatever it is. So let's just say that you bought 0 DVDs. You would get how much money back? So you would have $50. If you bought 1 DVD, 1 times 9 is 9, so it's 50 minus 9, which is $41. If I bought 2 DVDs, so 50 minus 18 would be what, $32, okay? So again, you're not buying a fraction portion of a DVD, so this would be an example again of a discrete domain. And if you were to say graph this again, and again I'll put these in units of 5. So I got 5, 10, 15, 20, 25, 30, 35, 40, 45, 50. So 0 comma 50 is right there. And then 1 comma 41, 5, 10, 15, 20, 25, 30, 35, 40. Looks like 41 would be right about there. 2, 32, 5, 10, 15, 20, 25, 30. So 32 is right about there. And again, the graph is linear, but you would have to take into account uh, that you can't buy, again, you can't buy fractional portions of the DVD, so that's why it is discrete. All right. Last couple things. It says they want to write a real life problem that fits the data shown in each graph. And then is the domain of each graph discrete or continuous? They want us to explain. Let's just look at being able to establish if the domain is discrete or continuous. So since I have points, I'm looking at a discrete graph here. And since I got a line segment for part B, this one is continuous. And that is being able to look at linear functions. Hope this helps. Until next time.